Now that you've looked at adding or partially adding up an arithmetic series, we're now going to look at adding up part of a geometric series. We're going to start with the part, and then eventually we're going to get to an infinite as well. So a geometric series itself is just an addition of successive terms of a geometric sequence. So we're going to have a geometric sequence of some sort, and then we're going to end up adding up a specific number of terms in order. So we have formulas for you to work on with this. S sub n again, because it's a sum, equals u sub 1, so your first term, times r to the n minus 1 all over r minus 1. This is one possible one. Or another way to write this would be s sub n equals u sub 1 times, you don't have to have the u sub 1 in the fraction, because it's all multiplication within there. So if I flip-flop these, 1 minus r to the n over 1 minus r, because what I did is I factored out that negative 1. This is the one that you will fairly consistently see used, but this one does work as well. Both of them are given formulas, and then you're able to plug in some specific values. So the first example that goes with this, find the sum of 3 plus 9 plus 27 plus blah, 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 to 10 terms. So we're finding the sum of the first 10 terms. First thing, I understand that we're working with geometric series, but you need to make sure that you're actually finding the sum of a geometric series, that it is geometric. So that's the first piece. Make sure you find what your multiplier is. You're going to need it anyways. In these formulas, you're going to need your multiplier. So if I go through, so what happens from 3 to 9, from 9 to 27? So each time it's multiplying by 3. So by doing that, it automatically is making sure, yes, this is geometric. It's not just something else. It's not arithmetic, for instance. So then I use my formula. So again, I'm going to use this formula over here. So it says my first 10 terms, which means I'm going to find s sub 10, my 10th partial sum. And that's u sub 1, which is my first term, times 1 minus my r value is 3 to the n, which is 10, over 1 minus r. So then I go through and do my computation. So keeping in mind order of operations, so this is 3 times 1 minus 3 times itself 10 times. Go ahead and use your calculator for that. And then 1 minus 3 is negative 2. Order of operations, super, super important. So next, before I go to multiply this into my calculator, do this first. 1 minus that value. You can triple that first or then divide it by negative 2, whichever order those two happen in. Either way, double check my math. Get 88,572. So again, just using your straightforward formula, plugging that in along the way. In the next example, for this one, we are finding the formula for s sub n, for the first n terms, which means I'm not actually going to get a value. In the previous example, it said find the sum of the first 10 terms, which is why we put the 10 up here. For this one, instead of placing a value in for n, we're going to have to leave it as n. So again, first and foremost, make sure you figure out if this is arithmetic or geometric, or if it's neither possibly as well. So going from the first term to the second term, so second divided by first is negative 1/3. Third divided by the second is negative 1/3. Therefore, my r value is negative 1/3. It's a multiplier, which means this is geometric. So I go through and I use my formula. S sub n equals, so u sub 1 times 1 minus r to the n over 1 minus r. So then just plugging in my information, S sub n equals, so my u sub 1 term is 9, times 1 minus negative 1/3 to the n. Be careful with negatives. The minus and negative, that's not here. The negative 1/3 is going to the n power. Exponents happen before subtraction. Or in that case, because it's going to multiply to it. Oh, 1 minus r. R again is that negative 1/3. In this case, now I can do the minus and negative because that's just subtraction there. There's no exponent on it. So now I just have to simplify processes down. Remember, you can't have fractions within fractions. That's not simplified. So this is 9 times 1 minus negative 1/3 to the n over, so 1 minus 1/3 is positive 4/3. Dividing, this is dividing. Dividing by 4/3 is the same thing as multiplying by 3/4. So this whole thing can be multiplied by 3/4. Doesn't matter where the multiplication goes if it's multiplication. So this is 9 times 3/4 times the whole quantity, 1 minus negative 1/3 to the n. And then from here, combine those together. I'm just cleaning this up now. We have some multiplication. So this is 27/4 times the quantity 1 minus negative 1/3 to the n. And then lastly, this isn't factored. It's kind of in factored form, but it's not factored because there are fractions. Factors have integers. So I can then distribute this through. So I get 27/4 minus 27/4 times negative 1/3, and that all goes to the n. This is my formula for f sub n. So I can now find the fifth partial sum, I can find the eighth, I can find the 20th, etc., using this formula instead of continually having to plug each of those values into this original one. It makes the problem a little bit easier. The math itself gets a little ugly along the way, but there's nothing spectacular about the math that happens there. So this will work for any sums that you're looking at. So if you're trying to find a finite sum, so the sum of the first so many terms, this is what you're going to use. Now, geometrics, we can also find infinite sums. What that means is I can add up every single term in my sequence in certain cases. I can do that if my r value, well, first off, if my r value is greater than 1, if it was an infinite series, it would diverge because that sum just keeps getting bigger and bigger and bigger and bigger and bigger. So if we had an r value, and it's the absolute value of it, so if it's greater than 1 or if it's less than negative 1. So if my r value, for instance, was 2, such as 3, 6, 12, etc., if I add this up, since each term that follows just keeps getting bigger and bigger and bigger, this is going to shoot off to infinity. It's going to diverge. There isn't going to be a specific number that it converges to. Versus, if r is greater than negative 1 or less than 1, then at some point it's going to approach 0 for very large numbers of n, which is why it's going to converge and have a limiting sum. So a value that's between negative 1 and 1, let's say r was 1/2. So we'll start with 8, and then my next term would be 4, 2, 1, 1/2, 1/4, etc., 1/8, 1/16. As you keep finding those numbers, as they keep increasing, that number becomes so incredibly small, we say it approaches 0. It's almost like adding nothing. Now, it technically is still adding something. It's just half of what it was adding before. So keep that in mind when you're looking at a problem like this. If I were to add up the infinite sum, if I added up every single possible value, there would be a number. Okay. However, it does keep going. So from the following example, you'll be able to develop a general formula for an infinite geometric series. So if we had 3 plus 3/2 plus 3/4 plus 3/8 plus 3/16, etc. So if we were to add this up for the entire problem, so if I was going to add up every single one of these, it will converge to a specific number. So in order to do that, I need to go back and check to make sure that my r value, if it's going to converge, my r value must be greater than negative 1 but less than 1. So I need to find r. So to find r, first off, I should realize if this is geometric or not. So I take the second divided by the first, 3/2 divided by 3, which is the same thing as multiplying by the reciprocal, which means that my R value is 1/2. And I can keep doing it. I can realize that 3 times 1/2 is 3/2 times 1/2 is 3/4, etc. So a couple ways to find your R value. So since it's greater than -1 but less than 1, I know this is going to converge. So now, if I put it into my formula, S sub n equals u sub 1 times 1 minus r to the n over 1 minus r, and I plug in each of my pieces of information. So I'm finding my infinite sum. So right now I'm just going to leave S sub n. I'll change that in a little bit. U sub 1, my first term is 3, 1 minus 1/2 to the n power over 1 minus 1/2. Now what ends up happening is when n gets really, really big. So once I've gone out to like 1,000,000 places, okay, I've added up 1,000,000 terms. What's my 1,000,000th term in the sequence? 1/2 times itself 1,000,000 times. So that's 1 to the 1,000,000th power over 2 to the 1,000,000th power is 1 over something really, really, really small, which means this approaches 0. Because it becomes so minuscule that when you continue to add them up, you get quite small numbers, which means there's no n left in here. Here, we'll leave that here. So no n in my equation anymore, so this is S equals 3 times, well, 1 minus 0 is 1. My denominator is 1 minus 1/2. Well, 1 minus 1/2, you can figure out is 1/2. But my generic equation, this is what our goal was, not finding the sum of it, but to find our generic equation. S equals 3 was my first term, which is u sub 1, times 1 over 1 minus 1/2 was my R value. So the convergent series for geometrics is u sub 1 times 1 over 1 minus r, or S equals u sub 1 over 1 minus r. Either of these are perfectly acceptable to use. So just quickly to finish off this problem, just so that you have practice with it, this is S equals 3 times 1 over 1/2. 1 divided by 1/2 is the same thing as multiplying by the reciprocal, so it's 3 times 2. Therefore, this converges to 6. So if I were to add up the infinite number of terms here in this series, it would be 6. So that's how you work with the two geometric scenarios. Finite, which is where I add up a partial sum, and infinite, which is where I add up every single possible number in the series.